Before we start, please remember to mute your microphone. For more information on Delta products, you can visit our YouTube channel. You can also visit our download center to get the latest manuals, catalogs, drawings, EDS files. I just put here a quick graph to show the different drives that Delta has released in the last 25 years. So drives are widely used across many industries, and it's always good to have the right product for the different requirements. So just very quickly, because the attendance today is quite advanced, so I'll just go very quickly through the first part. So I think you see a lot of names on the market for the same device. So sometimes you see variable speed drives, variable frequency drives, inverters, AC motor drives. Sometimes you see them as variable voltage, variable frequency drives. And most of the times they refer to the same device. So there's, I think, over 100 functions within a drive, but the fundamental one for which we call them variable frequency drives is because they take the fixed characteristics of the electrical grid and they turn them into controllable characteristics. So they take the fixed voltage and frequency, and then on the output you can control the amount of voltage and the frequency that you put onto a motor. So what is an AC motor, and why do we want to control the voltage and the frequency that is put on the motor? Well, you have quite a few different types of motors. So you have permanent magnet motors, induction motors, and more recently you can also use synchronous reluctance motors. They're usually made out of a fixed part called stator and a rotating part called rotor. If you have a look at the cross section, you can see that the motor is actually made out of thin laminations separated by insulation and stacked one upon each other. You can see here a complete list of all the components of a motor. Now, both PM motors and IM motors, so both permanent magnet motors and induction motors, work on the principle of the rotating magnetic field. So that means that the stator generates a magnetic field which pushes the rotor in a rotary movement. The speed of the rotor is proportional to the frequency that is supplied with. So a higher frequency will result in a higher speed. Now, the torque, which is developed by the motor, so that's the rotational force, that is proportional with the current that is going through the motor. So these are two basic principles which are very important to remember. So speed of the motor is proportional to the frequency that is supplied with, and the torque is proportional with the current that's going through the motor. Although it is a bit more complicated than that, but that's the basic of it. So how does a variable frequency drive works? So a rectifier, if you look here on the input, you have a rectifier which converts the fixed main supply voltage from AC to DC, and then the DC voltage is then converted back into a controllable AC voltage with the help of the inverter side. So this is a three-phase rectifier, what you see here. So for a three-phase drive, you can also use single-phase drives, then you have two less diodes on this side. Regardless of whether the input of the drive is three-phase or single-phase, this still gets converted to DC, so plus and minus, and the output is always three-phase. So this is one question which we get often: can we control single-phase motors? And the answer is no. No, the output is always three-phase, so you cannot use it with single-phase motors. Now, the sequence in which the IGBTs of the drive opens will determine the frequency that the motor sees and the duration. So how long are the IGBTs open, the duty cycle, that will determine the voltage that the motor sees. And when we talk about frequencies and variable frequency drives, we always refer to two frequencies. So one is the fundamental frequency, so which you can see here. That is the frequency which determines the speed of the motor. And this can be anywhere from 0 to 600 hertz on low frequency drives, or up to 2000 hertz on high speed drives. Now, another frequency that we refer to is the carrier frequency. And this is the frequency which helps build the fundamental frequency. So this is normally somewhere between 2 kilohertz to 15 kilohertz. So also if you look here, you can also see that you can have this from anywhere from 2 kilohertz to 15 kilohertz. And in order for the fundamental frequency, so that is this one, to have a somewhat acceptable form or shape, the drive needs to give a minimum ratio of 1 to 10 between the carrier frequency and the fundamental frequency. Okay, so we've gone through the basics of the drive. So let's talk a bit about what are some of the functions, what are some of the other functions that drives can do. So just want to mention that almost all of the functions that I will mention are supported on all of the Delta drives. If there is any particular function that you would like more information, then please feel free to raise your hand. You have a function in Zoom to raise hand, and then please feel free to ask. Okay. So firstly, you have PID control, which is very commonly used to control dynamic processes such as flow, temperature, pressure, level, and others. The way it works, you normally have some feedback sensors. These are somewhere in the range of 4 to 20 milliamps or 0 to 20 milliamps, 0 to 10 volts, etc. I think sometimes you also get the feedback through some communication protocols, so it doesn't really matter. In this type of applications, you do not actually care what is the speed at which the motor is running. So for example, if you are trying to achieve a pressure of 6 bars, then all you really care is that your pump will increase the speed when the actual pressure is below 6 bars and decrease the speed when it's above that. Yeah. And then you have the reason it's called PID because you have different gains, proportional, integral, and derivative, which you can set in the drive or in the onboard PLC of the drive. Another very commonly used function is the skip frequency. In many applications, you get a sort of mechanical resonance when the motor is running continuously at a particular speed. And the drive can help to prevent this situation by making sure that the drive never actually runs continuously at those particular speeds. So if you look here, you can set different bands which the drive will avoid. So this doesn't mean that the drive jumps directly from whichever frequency you set in 133. It doesn't mean it jumps directly to the frequency from 132. So it does go through that bandwidth. It just never actually stops at any particular frequencies in this area. So you basically set a lower limit and an upper limit. And yeah, this function is sometimes combined with the PID function. Next is the overvoltage stall prevention. In many applications, you can have that the load is actually pulling on the motor. So in those cases, the motor switches to generator mode. And in those cases, what happens is you actually get the energy back from the motor into the drive. if there isn't actually too much energy coming back from the motor, and if the application is not very sensitive to the time that it takes to stop, to bring the motor to a halt, then you can use the overvoltage stall prevention. And what this does is the drive monitors the DC bus voltage. And as soon as the DC bus exceeds a certain detection threshold, the drive, you can see here, stops from decelerating, just goes continuous. And as soon as the DC bus voltage drops again below a certain level, then the drive can start to decelerate once again. So in this case, if you compare with the actual set deceleration time, the stopping time will actually take a lot longer. So this function is definitely not to be used in applications in which the stopping time is sensitive. So definitely not for vertical applications, and definitely not for cranes, hoists, or whatever. Okay, but I do see this function commonly used in fans and other similar applications where the stopping time is not crucial. Then you have overcurrent stall prevention, and this is, in principle, it's very similar. It's just that this function looks at the output current, and it can, the drive can see when the output current is above a certain limit, it can actually decrease the output frequency in order to decrease the load on the motor. Now, very important to mention is that this function will only really work in variable torque applications. So variable torque applications are fans, pumps. These are applications in which if you increase the speed, then also the load increases proportionally. Actually, it's not proportional, it's quadratic. It does not work in applications which are constant torque. So in conveyors or other similar applications, it makes no difference if you decrease the speed. The output current will not really decrease that much. So keep in mind that this function can only be used on variable torque applications. Okay. Again, very popular with high inertia applications and with fans are the is the flying catch function or speed search. And what this function does is, if there is a power outage for, I don't know, 2 or 3 seconds or even more, some fans, if they have a lot of inertia, it can take even a minute or more to come to a complete halt. And you definitely do not want your application to have to wait for a minute or longer until the fan reaches a complete stop so that you can start it once again. So what the drive can do is when it's starting, it can detect what is the frequency at which the motor is currently running, and then it can just catch it from that particular frequency. So what you have in this oscilloscope, which I have here, is flying catch function on a PM motor, and this is running in PM sensorless. So there's no feedback, there's no encoder on the motor. It's just running in PM SVC. You can see there is a power down here. You can also see it in the DC bus decreasing. And then you can see it a few seconds later when the drive actually detects the speed of the motor and catches it at about, this is 25 Hertz, detects that the motor is actually running at 25 Hertz, and then it brings it back to its set point of 35 Hertz in this case. Another popular function is the energy saving function. I just recently got the chance to see what an important effect this function can actually have on saving energy. You can see that if the drive is running constantly at some particular speed, and the demand is actually low, so if the load on the motor is actually quite low, the drive can keep the frequency, can keep the speed at which the application needs to run, and it can automatically lower the output voltage, and this will proportionally lower the output current as well, thus helping save on energy. Now, as soon as some load is added on the motor, then you will also see the output voltage increase proportionally to the load that is being added. So these are all functions which are commonly used in variable torque applications. Do you have any questions so far? And if not, then I will move to the next set of functions. And these are more commonly used in constant torque applications. So very popular to use with drives is the mechanical brake control. So in this case, many times you get some mechanical brake attached to the motor. And what you can do is you can program the drive to engage and to release that mechanical brake depending on the output frequency and also on the output current. And you can set all of this through these parameters. Also commonly used with this sort of applications, if the motor is being run in open loop, so if there is no encoder connected to the motor, then you still need to make sure that you have enough torque at very low speeds. So for this, you normally use DC injection braking. And what this does, this injects a current into the motor, which makes sure that the motor develops enough torque so that as soon as you release the mechanical brake, the load does not sag or the load does not pull on the motor in the opposite direction. Also commonly used is the dynamic braking. So if previously we talked about the overvoltage stall prevention, which is here, in which applications which are not very sensitive to the time it takes to stop the motor can use this function. For this application, for applications where it's mandatory to stop the motor within a certain amount of time, you can connect a braking resistor to the drive, and then the drive can actually take all the extra energy that is coming from the motor, and it can convert that into heat, thus helping the motor stop a lot quicker than it normally would. Also common with this sort of vertical applications, and especially in elevator applications, are the S-curves. So you can set, aside from the normal acceleration and deceleration ramp, you can also set S-ramps, which helps smoothen out the transition from normal speed to accelerating to decelerating and other similar functions. And finally, you have the safety stop. Currently, our drives can meet safety integrity level 2. So the safety stop is for safe torque off. So this means that the drive ensures that as soon as a stop command is given, as soon as the safe torque off function is triggered, the drive ensures that the motor will absolutely not develop any torque. So This is our 2-channel STO. And of course, there's also numerous motor protection and phase loss detection functions. So either input or output phase loss. So all of this can be detected by the drive. So are there any questions so far? So I think we skipped very fast through the first part. If you think that you need more information on any part which I've just gone through, then yeah, please feel free to interrupt me. I'll go through Delta drives very quickly. Okay. So I see we have one question. How does the phase loss function work, since it can be powered on any phases? So I think firstly we need to clarify which phase loss are we referring to. So you can have input phase loss, and in that case, so let me switch back to. So if we are referring to the input phase loss, the drive will actually see that on the DC bus current. So when one of these phases is not connected, so for instance, if the S phase is missing, then the voltage that you will see on this side will have a much higher ripple, and the drive can actually detect that. But it's important to mention that this function will only actually work when you are actually running a motor. So at very low loads, it's impossible to detect because then you also have very low ripple. But as soon as you start adding some load, then the drive will detect that. It's very easy to do. And for the output phase loss, this is very easy to do. There's no software required or anything, because the drive can just see, because you have output current detection. So then you can actually see what is the current that's going through each phase. And if one of the phases has absolutely no current, or there's some significant current imbalance, then the drive can just detect that. Okay, so I hope that clarifies it. Okay, so I'll move on to the Delta drives overview. So firstly, I'll explain a bit about how the drive type numbers are constructed. So first 3 letters normally stand for variable frequency drive, but we also have active front end and regenerative drives. Following 3 numbers will show you the power of the drive. Then you have the drive series. So you have quite a lot of different drive series. Then you have the voltage. So in this case, 4.3 stands for 400 volt and 3 phase. And finally, you have the hardware version. So we always start with A, but if there is any update, then you get other letters. Now, as of 2016, with the release of the M300 series, we've actually changed the naming rule so that the type numbers are actually based on the output current instead of the power. And later on in this presentation, I'll go a bit into more details as to why it's important to size the drive based on current and not based on motor power. So the type number is more or less similar to the previous one. Just have the VFD for variable frequency drive. Then you have the current instead of the power. Then you have the drive series. Again, the output voltage. And then you have a few extra letters at the end, which will give you the IP protection level, whether or not it has a built-in EMC filter, whether or not it has a safe turn-off function, and if the drive is high speed or low speed. It's important to mention that due to different regulations, you have to treat the high-speed drives more carefully. It's very important to be careful where you actually export these drives. And then finally, you have the hardware version of the drive. So firstly, I can show you the ME300, which is the most recently released Delta drive. This is the economic version of the M300 series. You can have a read through the different specs and features of the drive. And if you have any questions, then you can let me know. So compared to the MS300, there's fewer inputs and outputs. There is no possibility to connect any field bus option. There's no built-in PLC, and it's up to 7.5 kilowatt or 17 amps. But you do have different pump functions, pump control. So you have functions for leakage and dry run detection, and also for multi-pump control. Then moving on, we have the standard compact drive, the MS300. This is similar to the ME300, but this time it can go up to 22 kilowatt. It has more digital inputs and more IOs. Very important, you can connect many field bus options, such as Profibus, CANopen, Modbus, TCP, or Ethernet IP. You have also high-speed models, which can go up to 1,500 hertz. So that is the fundamental output frequency. And as I've mentioned a few slides earlier, it's very important to keep a good ratio between the output frequency and the fundamental, between the fundamental frequency and the carrier frequency. So, of course, if you are running a motor at up to 1,500 hertz, then it's good to remember to set a carrier frequency which is at least 15 kilohertz. And when you do set a drive to 15 kilohertz, then it's also good to remember that there is some derating required, and we'll go through that a bit later in the presentation. Now, VFDE, this is one of Delta's most popular drives from the previous generation of compact drives, and I think it's still very popular on the market. You can see its standard digital inputs and outputs and the different functions. Of course, since it's an older generation, then its built-in PLC has fewer steps compared to the MS300, but it's still a very good function to have. And then we also have the equivalent for ME300, the VFDEL, the micro drive. Now, compared to the VFDE, it's good to mention that VFDE does not come with a built-in keypad. So normally the keypad has to be ordered separately. So that will be this one. And VFDEL does come with a non-detachable keypad. Now, moving on to our standard high-performance drive, so the C2000, which can run motors in field-oriented control, so that is with encoders. So we support a number of different encoders, like anywhere from ABZ to sine, cosine, and to resolvers and also encoders with commutation signals and all of that. You can use the drive to run PM motors or synchronous reluctance motors, and of course also induction motors. You have different functions for speed and torque and positioning control, also with feed forward. I think some of you are quite familiar with this drive already. So I'll not go into too much detail over it, but if you have any questions for it, then please feel free to ask me. And a bit later in this training, I'll also show you some master-follower functions with the C2000 and also some positioning control. So I just got one question, which says VFDE has I/O accessories, which is very useful, but the replacement, which is MS version, does not have that function. I'm wondering which. Oh yeah, you mean to? Okay, yeah, that the fact that you have different cards, optional extension cards, which you can install on the VFDE in order to get multiple inputs, so more digital inputs or more relays and all of that. For the M300 series, yeah, you cannot put any I/O extension module on the MS300 or ME. However, that will be supported in the MH300, which is the high performance variant of the M300 series. So in the future, this will be supported on the MH. And there is a second part to this question. Is there any other from the same range other than the C and CP? Yeah, so I just answered that. So the MH300 will support this. Okay, so I hope this answers your question. So then moving on to the CP2000. This is more or less based on the C2000 architecture. You can see it can go up to 630 kilowatt or up to 500 kilowatt in 400 volt. And this drive is mostly developed for variable torque applications, which normally require not a very low overload. So normally fans, pumps, and this type of applications, you normally see that they don't really need more than 100% or 110% overload. So that's why it's a drive designed for light duty or normal duty. You can also select that. Now, what's interesting about this drive is that it comes with a built-in backnet. This is BACnet 485, but there's also an option module for BACnet IP. So if you would like more information on that model, on that option, then please let us know. And because it's made for variable torque applications, then of course you get some specific functions like cascading, so control, and yeah, multi-pump control, multi-motor control. And of course you get different functions for intelligent pump control. And then I'll move on to the CFP 2000. This is our IP55 drive. And while the firmware is completely identical to the CP 2000, there are some significant differences in hardware. So for instance, the built-in EMC filter does not stop at 37 kilowatt, but it goes all the way up to 90 kilowatts. So that's up to that's through the whole power range of the motor. And also the built-in DC reactor is also present through the whole power range. So in the CP2000, it's only from 45 kilowatt and above. And at the moment, it comes only in 400 volt and up to 90 kilowatt. But there are, however, plans to develop 230 volt and 600 volt models. And finally, the last drive that I would like to talk about is the VFD-ED. So this is a drive specifically designed for elevator applications. So you have, it supports field-oriented control with an encoder card, and it supports different types of encoders, which are popular in the elevator industry. It also comes with built-in safe torque off up to safety integrity level 2. And also it comes with an emergency power supply input, which is also very important in elevator applications where you want to connect a UPS, an uninterruptible power supply, to the drive in case there is a mains power outage. And in those cases, you want the drive to detect which is the easiest way for the cart to move. Is it up or down, depending on the position of the counterweight? So the drive can do that, and then using the power from the UPS, it can slowly move the cart, the cabin, back to the next floor, so that anyone who's currently in the elevator can get out. Okay. So are there any questions so far? There are, of course, a lot more drives that Delta manufactures. So I've just gone through the more popular ones, but yeah, you can find all of them on our public website and in our catalogs. Okay, so if there are no other questions, then I will move on to the drive selection overview. So I just put here a quick graph to give you some idea of the different drives in terms of power and performance. First, you have VFD-EL and VFD-E, then still have the C200. Now, in terms of performance and functions, then of course, VFD-ED and C2000 are leading. You can also see the C2000 for 690 volt. That's a bit lower than C2000 because the 575 and 690 volts do not support field-oriented control, so they do not support encoder cards, and so that's the reason why you see it a bit lower on the performance and complexity chart. Then you also have the CP2000, of course MS300. So I mentioned previously the MH300, which is not currently released, but we expect to see it out next year. And of course, the CFP2000. Okay, so I think this is a very important chapter for anyone that is working with drives. So whether you are a sales engineer or if you are a field application engineer, I think it's very important to know how to select the right drive for the right application. So some parts can be quite simple. Yeah, you just check the motor current and then you select the drive based on it. But actually, there's a lot of subtleties to this, and it's good to be careful that you do not miss any important points. So for this exercise, I just highlight here a typical nameplate of an induction motor. So firstly, most importantly, you need to check which voltage is there actually available on site. Most motors are dual rated. So what you'll see here is that most motors you can connect either in delta or star for different voltages. So for instance, this motor can be run either in 400 volt or in 690 volt. And then, of course, also the rated current on the motor will be slightly different. Actually, not slightly, will be quite a lot different. So you'll select the drive depending on which voltage is available. So if you have 690 volt available, then yeah, you can choose a drive which is rated for that. It's important to mention that sometimes your network supply will not be exactly 400 volt. So it might be 380 volt or 460 or 480. But you can still select a 400 volt drive for that. You can check the input range in the user manual, but most of the time drives you'll be able to connect anywhere from 380 volt to 480 volt, and that's with a plus or minus 10 or 15% range. So here you have the different connection types that you can use, either for delta or for star. So it's important to keep in mind to size the drive always for the rated current, so which you see here. If, for instance, you go for a 400 volt drive, then you need to size a drive which can do continuously at least 29 amps. You should not necessarily look at the power rating, because in many cases, it will still be okay if you size the drive based on power. But in some particular cases, it can go very wrong, especially if you are working with some older motors with some really low efficiency, or if you are working with torque motors. And torque motors are very special in that they have a very high number of poles, which gives them a very high torque and a very low rated speed. So I can see, for instance, from this nameplate that this is a 4-pole motor for 50 hertz. But sometimes you get motors which are 8 poles or 16 poles or even 32 poles. In that case, the frequency is much lower, but the torque is actually higher, a lot higher. And if you remember, I mentioned in the beginning of this training that the output current is actually proportional to the torque. So in those cases, you will see a current which is much higher than what you would see here. So for the same amount of power, you get a actually much higher current. And in those cases, if you size the drive based on power, then that will most definitely not be enough. So the drive might not be able to deliver the amount of current that the motor needs. Okay, so it's very important to keep this in mind. So never size the drive based on power, always size it based on output current. Also, very important to keep in mind is to check the overload requirements. So normal fan and pump applications, they don't really need so much overload. But if you are using the drive on a vertical application, yeah, so if you're using it on a hoist or on a crane, then overload becomes very important. So sometimes you need 180% or even 200% if overload if you are working with a crane or an elevator. So in those cases, if you size, for instance, the wrong drive, then it can happen that you just get an overcurrent fault because the drive will not be able to deliver the overload that the motor requires, that the application requires. Also, some other factors to keep in mind when you size a drive is the temperature, the altitude, and the required carrier frequency. So for temperature, that's quite easy to imagine because the higher the temperature, the less, the more you need to dissipate the heat from the drive. But for altitude, this one is also very important to keep in mind. So if the end user, if the installation is somewhere at some really high altitudes, over 1,000 meters, then you also need to derate for that. And we have some derating graphs for each 100 meters or so, then you have to derate by a certain percentage. Because what happens at higher altitudes is that cooling becomes less efficient. So this is something which you have to keep in mind for basically any electronic device, not just for variable frequency drives. But what is specific to drives is the carrier frequency derating. So of course, it makes sense that if you use a higher carrier frequency, then also the drive is working a lot more and generating a lot more heat. So if you need to use a carrier frequency which is above the rated one of the drive, then we also have different graphs in the user manuals in which you can consult and which you can see which derating is actually needed. And if anyone is not 100% clear on this, then please let me know. We can go through some examples right now of how to do these deratings. And if not, then we'll just move on. So finally, we also need to check what functions are actually required. So make sure if the application needs the drive to control some mechanical brake, or if the application needs to use different functions, you have to actually check the user manual to see if those functions are being supported by the drive. Okay, so I got one request to do an example on carrier frequency. Okay, so let me open up the user manual. So I will open up, let's say, if we use, for instance, this motor here, I'll say that we choose a 400 volt drive, 29 amps. Let's say that this is a spindle motor application. So spindle motors can go at some very high frequencies. And when you go at high frequencies, like I mentioned, you have to use also higher carrier frequencies, okay? So if you use a high carrier frequency, then you also need to do some derating. So let's say that I use an MS300 drive in this case, and I'll size it for this motor, 29 amps. Yeah, spindle motors can vary anywhere between 400 hertz up to 2000 hertz. So if I say that instead of 50 hertz, if I say that this motor is rated, for instance, at 1000 hertz, then I need a carrier frequency of at least 10 kilohertz. Yeah, if I have a motor which is here 100 hertz. So for 1000 hertz, I need to select a drive which is high frequency. So in this case, I will check the MS300 high-speed models. So this motor being 29 amps, I need, I'm looking at the 400 volt models. I see we have 25 amp models. So I will look at the 32 amp drive, yeah? But since I'm using it at 10 kilohertz, I'll definitely need to derate, because you can also see here that the default carrier frequency is 6 kilohertz, yeah? And I need to use it at 10 kilohertz. So I will scroll down a bit, and I will find the derating graph for carrier frequency, which is which is here. So this is in the description of parameter 655. So of course, it also depends if I'm using the drive in a 50 degrees environment or in a 40 degrees environment. So in this case, if I use it in a 50 degrees environment, then I would need to have a derating of at least 75%. Okay, so then if I use the 32 amp drive, so I have 32 amps times 0.75. This will be 24 amps. And then if I compare this to the rated current of the motor, 29 amps, we can see that this is actually not enough. So I will have to use a slightly higher drive. So if I go back to the different models, I can see 400 volt, 32 amps. So a 38 amp drive might be sufficient for this case. Yeah, not quite. Yeah, in any case, the in this case, it's very close, but not quite. So you would have to use actually a 45 amp drive in this case, but also for a spindle motor, which is rated at 1000 hertz, yeah, you can expect that the rated current will be slightly different. But yeah, in any case, this is the principle to which you size a drive based on carrier frequency. So I hope this answers the question. So if there's no more questions on this particular topic, then I will move on. So aside from checking which functions are required in the drive and checking the brochure or user manual to see if they are actually supported, you also have to check for the required IP protection. So in most cases, you install drives in some electrical cabinet, and in those cases, IP20 is okay. But in some cases, some installations will just install the drives very close to the motor, and in those cases, you need around IP55, and you can use the CFP 2000 drive. You also need to check how many inputs and outputs does the application need. So see if the drive actually has that, or if you need to use some IO extension, or if you, yeah, if it's maybe more convenient to use a different drive or just use an extension module. Also important to check if the drive actually has to communicate with other devices, and what is the communication protocol that needs to be supported. And also very important is to check if there are any requirements from the application in terms of total harmonic distortions or in terms of electromagnetic compatibility. Okay, so that is about it on the presentation. So are there any questions so far? If there are no questions, then I will do a bench demo on the C2000 and on the MS300. And if you also have anything prepared on your side, if you have an MS300 drive, then you can also let me know, and then we can go through the setup and configuration together, okay? So, yes, Mats, you raised your hand.
I just want to tell you that we have an MS300 and the software connected.
Oh, okay, okay, that's good. Then firstly, I'll just go through some demos on the C2000, and then towards the end, we'll also connect with MS300, and we'll do some scopes, and yeah, maybe also go through using the MS300 to send different Modbus commands to the drive, like start, stop, and all of that. I don't know if you ever used this function on VFDSoft. So here I have two C2000 drives connected. So I would like you to notice the different terminals which you can get on a normal PG card, on a normal ABZ PG card. And if I will just share my camera right now. So hopefully everyone can see my configuration right here. So I have two C2000 drives. Both of them have a PG card connected. So you can see here on a PG card, on a standard PG card, you normally have the PG1 terminals, which are the terminals on which you input your encoder signals from the motor side. So with these signals, the drive uses to run in field-oriented control. Then you have the PG2 terminals, which are on this side. So you have A naught, B, and B naught. And these are the terminals which the drive uses to follow a certain pulse train or another drive. You can see that since this is the master drive, there's nothing connected to these terminals. And here you have the output, the PG out terminals. And these are the terminals which the drive uses to send out the output, the PG signals, which it gets on PG1, which you can see here. Okay, so whatever the drive gets from this motor, from this encoder in here, it will output on these terminals. And then I've wired the PG out terminals from the master drive to the PG2 terminals on the follower drive. Yeah. And I've configured them in a master follower setup so that you can see that the follower drive can just follow any position that I give it with the master drive. And currently the follower drive is set to listen to the position of to try to follow the position of the master It can also try to follow the speed of the master, but yeah, since it's a C2000, it's more performant to actually follow the exact position. So you can monitor here the actual motor position. So here is 34 and also 34 or 35, and then yeah, can move it. The drive more or less follows it accurately. And this is actually quite easy to set up. It only really involves a couple of parameters. So I'll just go through them very quickly. Firstly, you need to set parameter 1016. You need to tell the drive that the reference pulses are A and B type. You can have different types of pulses. You can also have that B-type leads, and yeah, you can also have just A and forward or B and forward type of pulses. So pulse and direction. And also you can put this on the MI8 terminals, but in that case, yeah, and in that case, you don't need a PG card. But yeah, the disadvantage in that case is that you can only really run it in speed mode, since you cannot run it in FOC PG if you do not have a PG card. Okay, so 1016, it's very important to set. Since the follower drive is running in positioning mode, you actually need to define this in parameter 0 -10. Yeah, so you need to set it to 1 to position mode. And of course, if you're running in positioning, then you also need to run in field-oriented control for PG. You need to tell the drive which should be the source for the control. So you need to set parameter 020 to 5 to PG reference. And finally, since we're running the follower drive in positioning mode, you need to also tell it what is the source of positioning. So then you have 11, not dash 60, but 11 dash 40, I think. Yeah, then you have 11 dash 40 source of positioning, and you need to tell the drive that it's coming from an external pulse. And this is basically it. So after you configure the drive in field-oriented control mode, you just need to set these 4 parameters, and you're ready to start. Yeah, and you can also set different ratios between the master and follower. So right now it's a 1-to-1 ratio, but you can also set it to you have some electronic gearbox parameters, so electrical gear. And depending on the ratio between these two parameters, 1017 and 1018, that's what the that's also what the follower drive will follow. So if I set, for instance, a 2-to-1 ratio, then for every 1 rotation, I can get 2 rotations on the follower, or even more. I also get with 10 rotations. There are, of course, more drives, more settings that you can play with. So, for instance, also the current gains. It's important to be able to configure so that you can actually determine how strongly the drive reacts to a change in load. Okay, so you can also set a smaller ratio between the between the master and follower drive. So if I set this to 50, I hope you can see. I'm not sure if it's actually very clear on your side. So if I do this, then maybe it's clearer. Yeah.
Vladimir, sorry for interruption. There is a question. Can you have a look, please?
Yeah, sure. Yes. So what is a PG card? So PG, I think maybe the origin of the PG is for pulse generator. So PG is basically an encoder card. So it's this card over here. So this is an extension card. This does not come with the drive as a standard. So you need to get this separately depending on which encoder type you are using. Okay, so I hope this answers the question.
Yeah, it does. Thank you.
Oh. Okay, so yeah, so if I set this to 50, then I get a completely different ratio between the follower and the master drive. So do you have any questions on this particular topic? And if not, then I think we can move on. So next, what I will do, you can see here, I also have an Ethernet IP card connected to this drive, to the master C2000. So I have it connected here. And I'm also connecting my laptop to this switch. And then this is also connected to an AS200 PLC. I don't know if you can see it. It's somewhere behind here. So what I will do in this case is I will use Ethernet IP to control this master drive in point-to-point mode. So I'll just set the different position command and the drive will follow it. So I'll just show you how quickly this can be done. Also, one important aspect which I've not mentioned with my previous configuration is that, so we are running, in this case, the follower drive in point-to-point. And I mentioned that you can also run it in speed control. You can also run the follower in speed control, but in those cases, you have to remember to lower or to disable completely the acceleration ramps on the follower drive, because the drive is already following the acceleration and deceleration of the master drive. So in those cases, the acceleration, deceleration, and also the S ramps will just be added on top of the master's acceleration and deceleration ramps. So then you might see some delay between the follower and the master. Okay, so moving on to how to connect to the drive with Ethernet IP and control it in point-to-point. So firstly, I will open COM Manager. So this is one software which I think most of you are already familiar with. So I have here with me the newer version of COM Manager, but which will be used on the future generation of software, DIA Studio. But so this version is not yet released, but it's, in terms of working principle, is exactly the same as the official version. So I'll just define a new driver. I'll select the configuration via Ethernet. And yeah, almost forgot to connect my laptop to it. Okay, so I select my network adapter, just click on search, and it should be able to find the AS PLC and also the Ethernet card on the C2000. So I think I've not connected properly. Yeah. Always works better when you connect your laptop to it. Yeah. So I'll just save this. So now I saved it with the generic name driver. So I will open VFDSoft. I will define here the, I will select here the PLC. So this is the driver, which I just created. And this is the IP address of the AS200 PLC. So I will connect to it. I will use that as a connection. And this is, I'll create a new project. So AS228T, which is also the PLC that I'm using. So I will define a new program here. So new cyclic task so that the program can get compiled. And I will go to hardware configuration. This takes a few seconds. So it opens up here. And now I can right click on my PLC and click on EIP Builder. So yeah, first I need to save the project. And then EIP Builder will open up. So here I can see my PLC. I can scan the network. And it should be able to find my communication card. Yeah, so that's here. I will add it to the same network. So now we'll go to data mapping. And this part is maybe not so intuitive. So maybe sometimes it might be more difficult to find, but you need to move your mouse cursor in this area and then right click on the PLC and click data mapping. So here I can define my input and my output registers on the AS300. And here you can see the corresponding registers on the C2000. So I'll just put that my, my output, my inputs are starting from D1. And my outputs start from D101. I only have one device, so I'm not so, don't really care about leaving a lot of unused registers. And then here I can see the standard definition of the inputs and also of the outputs. So this is what I can read by default. And keep in mind that this is cyclic reading and cyclic writing here. So I will just get two more registers, which are not in the default list. So I will look for 222C and 222D. So this will be the motor's actual position. Yeah. And I will take a print screen of this so that I can see it a bit later. I'll move this this side. It's always good to have your inputs and outputs handy. Okay, and I'll also take a print screen of the outputs. So I have this here. Okay, now I will download this configuration to the PLC. all done. And I can see that my configuration is okay. So if you get this green box, then everything should be okay. So now I'll close Ethernet IP Builder. I'll save the configuration. I'll also download here in the hardware configuration. Okay, so now if everything is okay, I'll close this and I'll save it. So now I'm back to my PLC program. So before I actually write anything, from a drive side, it's just easier to create a monitor table and just to read and write the different registers from this side. So I'll double click on this screen and I'll just start with D1. And if I look at the registers that I saved, I can see that it's up to 27. So I'll write here from D1 up to, let's say, 28. Okay. So these are going to be the addresses that I read from the drive. So these are going to be these ones, which I defined here, starting from D1. And now I want to also add the addresses in which I will write to the drive. So I start with D101. And I will need, let me see, I will only need around 12, yeah. Okay, so if everything is okay, then I will go online and I should be able to read all the different values that are coming from the drive, like the DC bus and status word and all of that. So you can see it here. So I have in D6, I have the DC bus value of the drive. So that's 312. There's no decimal point, but so that's why you see it as 3000, but it's actually 312 volts. And you can see here what else we have. So that is the DC bus on D6. And I should have on D26 and D27, I should have the actual motor position. Yeah, you can see here D26, the low word, and D27, the high word. And if you check here, you can see the actual motor position, it is here. And since you can read it also as a 32-bit value, you can see that the current position of the motor is minus 79,745. And if I switch back to the drive, so hopefully you should be able to see this also here. I hope this is clear. So 79745. So that's also what I'm seeing on the screen here. So first thing that I want to do is I want to check the definition of the control word and of the status word. And for positioning the C2000, you can use only the 6000 definition. So I will just open that up. I got this from the Profinet user manual, but actually the definition of the 6000 addresses is the same. So you can use this. You can use this for Profinet or for Ethernet or also for Profibus and also for Modbus TCP. At the moment, it's only not supported on EtherCAT, but that's also going to be supported in the near future. So this is my definition for the status word, 6000. So I can see here I have servo on bit 7. And to actually move to position, I have bit 0, okay? So when I set bit 0, then the drive will move to whatever position I set, okay? And I have here bit 2, which I can use to switch between absolute or relative positioning. 0 is relative and then 1 is absolute. So firstly, I need to see where exactly is 6000 defined in here. So I can see here in the print screen I took, it should be on bit on D105, okay? So if I set this to, if I set bit 7 to 1, then I should also see it in the status word. So status word is for 6000 addresses, 17. So D17 should see that. So if I set this, so you can see I can enable the drive or disable it from bit 7. And then I can write different different positions in 6004 and 6005. So do it from here. So if I go to D109, I can just write this as a 32-bit value. So currently the drive is set for a 2500 pulses per revolution encoder. So that means if you have 2500 pulses per revolution, that means that the drive will actually count 10,000 per one revolution. So that's for every pulse rising edge and falling edge. So if I want the drive to do one rotation, I can just set it to 10,000. Okay. So this will be my relative position command. And then I can just go back to 6000. So I still have servo 1, and I'll just ask the drive to move to by one rotation. Yeah, sorry, my bad. I just realized what I forgot. So it's actually really important. If you look through the description of the different registers, you see 6000, but you also see here 6001. So that's the mode of operation. So 0 is velocity mode. And yeah, you can also see it here in 6001. You can actually read what is the current mode. So if I read it in 6001, that should be in a D18. You can see here that it's 0, so that means for speed mode. And yeah, I actually need to set it to positioning. So firstly, I will stop the drive because you can only change operating mode when the drive is in stop mode. So just set it to 0. Now I'll set 6001 to 1 to positioning mode. Okay. So now I can also read it here. Now the drive is in positioning mode. Okay, so that was actually the problem. So I actually forgot to set it in positioning mode. So yeah, now if I just give the drive a frequency command, can actually see the drive moving. to its target position. So if I give it another run, you can see it actually moved, this time to position 100,000. So I'm giving it in 50,000 pulses. So that means that the drive is moving in relative movement every time I give it the command to move to a new position. And if I share my configuration, then you should also see this. So I will just give it a new run command. So you can also see it here. Now it's at 200,000. It's just going into different increments. I can also set the drive to move in absolute positioning. So instead of incrementing to 50,000 every time, I can just set it to move to this position, to the absolute position, 50,000. So right now it's at 250. So if I enable this bit, then when I trigger a new position command, then you should see that is not happening because I have not sent the drive to the home position because I've not done a homing on this drive. So it's very important to keep in mind that if you want to do absolute positioning, then first you need to do a homing procedure. And you can actually see this on the drive as well. You can see that I get an error message called NHOY, so which means that the drive has not been homed. So what I'll do is I will initiate, well, firstly, I will stop the drive so that I can reset this warning. So I will start the drive again, and I will do a homing procedure. So I just enable bit 47, and then you can see currently it's set to home at the current position. So now I can actually do the absolute homing. Okay, so one question I got is, do you need to do motor tuning when using positioning mode? Yes, that is absolutely mandatory. So in this demonstration, I just started directly with the motor pre-configured. But if you want to do positioning, then you absolutely have to enter the motor nameplate, to do an auto tuning, to set the encoder details into the drive, and then to set the drive to run in field-oriented control for PG cards. So let me see if I can just show this. So you can only really do positioning with these two modes. So if you go to parameter 00-11, velocity mode, you can only really do it with 4 or with 3. So IM FOCPG or PM FOCPG. You cannot do it with any other mode. You cannot do it in SVC sensorless or VF. So it's mandatory to have an encoder. Okay, so I hope this answers the question. So I can also set some different position commands. So if I set, for instance, then I can also set it to go to whichever absolute position I wanted to go. Okay, so are there any questions, or is there anything that you would like to see with this function, with the positioning? And if not, then I will move on to connecting with the MS300 with VFDSoft. So if you have any questions in the future, please don't hesitate to ask about this topic. You can, of course, do positioning from the digital inputs, from communication, or from also external pulses, like you could see that on the follower drive. So yeah, and also you can have different types of homing also supported for homing based on origin or positive, negative limit and all of that. Okay. So if there is nothing that you would like to see on this topic anymore, then I will move on to the MS300. So in this case, what I use is a simple USB cable. You can just connect directly to the drive. You don't need to use any external tool. And that's it. You just connect that to your laptop and you are ready to go. Okay, so firstly, you just need to find out which COM port has been assigned to your drive. So you can go to Device Manager to find out. So in this case, it will be COM port 3. And this is the default address of the drive. And you can change this if you want from parameter 9-01 and 9-04. So I'll just do a quick test. I can see that yeah, I'm connected properly with the drive based on this green LED. Then I can go to parameters and I can just read all the parameters from the drive. So it's more or less default, aside from a few settings. So you can also control the drive from VFDSoft if you want to. You just need to set the source of frequency to 1, that's RS485, and the source of operation to 2, that's also RS485. So if you do this on your side, then you just have to click on Write Select or Write All and press OK. Oh, in the meantime, I see there is another question. So in point-to-point mode, can you use parameter 415 and 416 to set a command from the drive only? Yes, that is possible. You can have a different, a range of different combinations for the digital inputs, and then you can just, send the drive to a position based on those parameters. In fact, we have a quick guide on that. I will open it. Let me see. So I'm not sure if you've seen this document, but you can find all the different configurations that are available for position control. And so what you were looking at was the positioning from the digital input. So depending on whether or not you're using an induction motor or a PM motor, you'll have different, graphs here. So in this case, you are referring to positioning from the digital inputs. So that will be here. Yeah, you can see here, point-to-point positioning. So you configure your digital inputs to the multi-step speed or position. And then you also have to configure one of the digital inputs to 88, and that is to actually trigger the movement to whichever position you have defined. And you can set the different positions in these parameters. Okay. And of course, you need to set the source of position command, 1140, you need to set to 0 so that the drive knows what it's actually looking for. And then you have a number of different parameters which you can set to control how strongly the drive reacts to different configurations. Okay. So I hope this answers the question. So moving back to VFDSoft, yeah, you can just read and write different parameter files from the drive. And more importantly, aside from this, you also have a trend function which you can use. So I also have the keypad. So because I set the drive to RS485, I can actually control the frequency on the drive with VFDSoft. So I can just give the drive a run and a stop command. But yeah, actually I also need to start the monitoring. So click start and go back to the keypad. If I click on fit all, you can actually see the drive and see the output frequency versus the frequency command. And I can also monitor the start and the stop signals. So you can see here when I gave a stop signal versus when the drive actually stopped. You can see the acceleration ramp, and you can also monitor how long it takes between two different points. You can see this on this side here. You can see from 0 Hertz to 19 Hertz. It took around 4 seconds. You can see that here. And it's for us here in technical support, it's always vital that we get this sort of information from your side. And also if we get the corresponding parameter file, that way we can more or less have some idea of what is actually happening on site. And you can also monitor different parameters here. And VFDSoft actually monitors all of these parameters at one time. So if you click on output voltage, you can also see the drive increasing the output voltage up to the corresponding VF curve. Because the drive is running in open loop, then it just follows a linear VF curve. So you can see the output voltage increasing proportionally with the frequency up to a maximum of 84 volt. And yeah, so that's about it on the trend function. There's really not that much to show on this. You can also save this information and load different trend functions. So it's easier to send by email and then to investigate what is actually happening. Okay. I can also show you, if you want to test the different configurations, the different Modbus addresses of the drive, then you can also do it with the advanced function here. You can just enter here any ID address and what do you want to do? Do you want to read or do you want to write into the drive? So you can just read the status word, which I can see at the moment is 0. I can write into the drive. I can write to the 2000 address. And for that, I just need to check what is the definition of the 2000 address. So I can see that if I want the drive to run, then I just need to enable bit 1. So I will just set this to 2. Yeah, and I don't know if you can hear that, but I can see the drive starting. So now if I read the status word, 2100, I can set this. Oh, sorry, that's Once again, my bad. 2100 is actually the warning code. It's not the status word. So what I need to read for the status word is 2101. So that is the status word. 2100 is just the error and warning code. So that just shows you if there is any warning on the drive. So I will read that. And yeah, I can see different bits which show me that so bit 1 and bit 2 are on. So that means that the drive is in run mode. Yeah. Okay, and we can also set the different frequency commands. In this case, it's in 2001. So if I just go here, 2001, I can set the drive to 500, which should correspond to 5 Hertz. Yeah, and that just moves the drive to 5 Hertz. And I can also share that with you. And if I change this to 1000 and click on send, should be able to see it on the drive. So this function is quite useful to see if you have a good connection, if communication is okay or not, and to see if you are reading and writing the correct registers. So I think this should be about it. If you have any questions, then please let me know. I can try to answer. If there are no questions, then I think we can end the meeting now. Okay, so there doesn't seem to be any questions. So thank you for your time. Thank you for joining me. I hope this was useful to you. And if you have any questions in the future, then I think most of you already know how to contact me or how to contact us. So thank you again and have a nice day.